What if the next chapter of human history isn't written on Earth, but among the stars? Imagine a future where humanity has spread beyond our pale blue dot, transforming distant worlds into new homes. This isn't science fiction, it's a possibility that scientists and futurists are actively exploring. Today, we're diving into 25 groundbreaking theories on how exoplanets could be terraformed for human life. From manipulating atmospheres to creating artificial magnetic fields, these ideas push the boundaries of what we think is possible. Whether it's melting ice with orbital mirrors or seeding alien oceans with Earth's microbes, each theory offers a glimpse into a future where humanity becomes an interstellar species. So, buckle up, because by the end of this video, you'll not only understand the science behind these incredible ideas, but also see how close we might be to making them a reality. Let's explore the future of humanity among the stars. Now, let's take a closer look at the first theory, atmospheric manipulation. This idea revolves around the concept of transforming an exoplanet's atmosphere to make it suitable for human life. Think of it as giving a planet a complete makeover, turning it from a hostile environment into one where we can breathe, work, and thrive. The key to this process lies in three main steps: introducing oxygen, reducing harmful gases, and stabilizing atmospheric pressure. First, let's talk about oxygen. On Earth, oxygen makes up about 21% of our atmosphere, and it's essential for our survival. To create a breathable atmosphere on an exoplanet, we'd need to find a way to produce oxygen in large quantities. One method scientists have proposed is using photosynthetic organisms like plants or algae to convert carbon dioxide into oxygen. Alternatively, advanced technology could be used to split water molecules into hydrogen and oxygen, releasing the oxygen into the atmosphere. Next, we need to address harmful gases. Many exoplanets have atmospheres filled with gases like carbon dioxide, methane, or even ammonia, substances that are toxic to humans. To make these planets habitable, we'd need to remove or neutralize these gases. One approach could involve chemical reactions that convert harmful gases into safer compounds. For example, carbon dioxide could be turned into carbonate minerals, effectively locking it away and reducing its presence in the atmosphere. Finally, stabilizing atmospheric pressure is crucial. Too much pressure and humans would feel like they're being crushed. Too little and our bodies couldn't function properly. Achieving the right balance would require careful adjustments, possibly by adding or removing gases to reach a pressure level similar to Earth's. This might involve releasing inert gases like nitrogen or argon to create a stable, breathable mix. Atmospheric manipulation is a fascinating concept, but it's not without its challenges. The sheer scale of the task is staggering. Altering an entire planet's atmosphere would require immense resources and time. Plus, we'd need to ensure that any changes we make are sustainable in the long term, preventing the atmosphere from reverting to its original state. Still, the idea of transforming a distant world into a second Earth is an inspiring vision, one that could redefine humanity's place in the universe. Now, let's shift our focus to the challenges of atmospheric manipulation. While the idea of transforming an exoplanet's atmosphere is thrilling, it's far from simple. One of the biggest hurdles is the sheer amount of energy required. Altering an entire planet's atmosphere isn't like flipping a switch. It would demand an unprecedented level of power. For instance, producing oxygen on a planetary scale would require massive infrastructure, whether through biological means like algae farms or technological solutions like water-splitting machines. The energy sources needed to sustain these processes would have to be both reliable and sustainable, raising questions about how we'd generate and maintain such power over centuries. Another critical challenge is the risk of runaway greenhouse effects. Imagine this: we introduce greenhouse gases to warm up a cold exoplanet, but the process spirals out of control, trapping too much heat and making the planet uninhabitable. This isn't just a theoretical concern. We've seen similar effects on Earth with climate change. On an exoplanet, the stakes are even higher, as we'd be working with an environment we don't fully understand. A single miscalculation could lead to catastrophic consequences, turning a potentially habitable world into a scorching wasteland. Time is another major factor. Creating a stable atmosphere isn't something that happens overnight. Even with advanced technology, the process could take hundreds, if not thousands, of years. During this time, we'd need to maintain constant oversight to ensure the atmosphere evolves as planned. This raises practical questions. How would humanity sustain such a long-term project? Would we need to establish permanent colonies on the exoplanet to monitor and adjust the process? And what happens if unforeseen issues arise over such an extended period? These challenges highlight the complexity of atmospheric manipulation. It's not just about the science, it's about the logistics, the risks, and the patience required to transform a distant world. Yet, despite these obstacles, the potential rewards are immense. Successfully terraforming an exoplanet could open up new frontiers for humanity, offering a second home among the stars. As we continue to explore these possibilities, it's clear that atmospheric manipulation is as much about innovation and perseverance as it is about science and technology. Now, let's turn our attention to another fascinating approach: greenhouse gas seeding. This theory revolves around the idea of introducing greenhouse gases to a cold exoplanet, effectively warming it up to create a more hospitable environment. Think of it as giving a frozen world a cosmic blanket, trapping heat and gradually raising temperatures to levels where liquid water and potentially life could thrive. The types of gases used in this process are crucial. Carbon dioxide is a prime candidate, as it's a well-known greenhouse gas that effectively traps heat. Methane is another option with an even greater heat-trapping capacity, though it's less stable over long periods. Sulfur hexafluoride, a gas used in industrial applications on Earth, could also be considered due to its extreme potency as a greenhouse gas. Each of these gases has its own advantages and challenges, and the choice would depend on the specific conditions of the exoplanet in question. However, the long-term effects of greenhouse gas seeding are a double-edged sword. On one hand, it could transform a frigid, icy world into a temperate paradise. On the other, there's the risk of overdoing it. Just as we've seen with climate change on Earth, an excess of greenhouse gases can lead to runaway warming, turning a planet from cold to scorching in a relatively short time. This delicate balance requires precise calculations and careful monitoring to avoid tipping the scales too far. Another consideration is the sustainability of these gases. Some, like methane, break down over time, which could mean needing to replenish them periodically. Others, like carbon dioxide, might require ongoing management to prevent excessive buildup. The challenge lies in creating a stable, self-regulating system that maintains the right temperature without constant human intervention. Greenhouse gas seeding is a bold and ambitious idea, one that could unlock the potential of icy exoplanets scattered across the galaxy. Yet, as with all terraforming theories, it comes with its own set of risks and uncertainties. The key will be finding the right balance, enough to warm a world, but not so much that we lose control of the process. As we continue to explore these possibilities, it's clear that the future of terraforming will require not just scientific ingenuity, but also a deep respect for the delicate systems that govern planetary climates. Now, let's shift our focus to a critical aspect of greenhouse gas seeding that goes beyond the science: the ethical implications. While the idea of warming a cold exoplanet to make it habitable is undeniably exciting, it raises important questions about our responsibility as potential planetary engineers. What if, in our efforts to create a new home for humanity, we inadvertently harm or destroy existing ecosystems, no matter how primitive they might be? One of the most pressing ethical concerns is the possibility of disrupting or erasing native life forms. Even if an exoplanet appears barren or lifeless, we can't rule out the existence of microbial life or other organisms that thrive in extreme conditions. By introducing greenhouse gases and altering the planet's climate, we risk wiping out these life forms before we even have a chance to study them. This raises a profound moral dilemma. Do we have the right to prioritize human survival over the potential existence of extraterrestrial life? Another ethical consideration is the concept of planetary stewardship. If we begin terraforming exoplanets, we're essentially taking on the role of caretakers for entire worlds. This responsibility comes with immense power and the potential for irreversible consequences. For example, if we miscalculate the amount of greenhouse gases needed, we could trigger runaway warming or other unintended effects that render the planet uninhabitable for both humans and any native life. The stakes are incredibly high and the margin for error is slim. There's also the question of equity and fairness. If humanity gains the ability to terraform exoplanets, who gets to decide which planets are altered and how? Will this technology be accessible to all, or will it be controlled by a select few nations or corporations? The potential for conflict over planetary resources is a real concern, and it's one that needs to be addressed before we take any concrete steps toward terraforming. Finally, we must consider the long-term impact of our actions on the galaxy as a whole. Altering the climate of one exoplanet might seem like a small step, but it sets a precedent for how we interact with other worlds. If we approach terraforming without careful thought and respect for the environments we're altering, we risk repeating the mistakes we've made on Earth, exploiting resources without regard for the consequences. As we explore the possibilities of greenhouse gas seeding, it's clear that the ethical challenges are just as complex as the scientific ones. Balancing our ambitions with a sense of responsibility will be key to ensuring that our efforts to terraform exoplanets are not only successful but also morally sound. With that in mind, let's move on to another intriguing theory: the use of orbital mirrors to melt ice and create liquid water on distant worlds. Now, let's turn our attention to a fascinating and visually striking idea: using massive orbital mirrors to melt ice and create liquid water on distant exoplanets. Imagine enormous mirrors positioned in space, reflecting sunlight onto a frozen world to warm its surface. This concept, while seemingly straight out of science fiction, could play a crucial role in terraforming efforts by transforming icy landscapes into habitable environments. The basic principle behind this theory is relatively straightforward. By placing large mirrors in orbit around an exoplanet, we could direct concentrated sunlight onto its surface, gradually melting ice caps or frozen oceans. This process would not only create liquid water, a vital resource for life, but also help regulate the planet's temperature, making it more suitable for human colonization. The mirrors could be adjusted to control the amount of sunlight reflected, allowing us to fine-tune the warming process over time. However, the engineering challenges involved in this approach are immense. First, constructing and deploying mirrors of the necessary size would require advanced materials and construction techniques. These mirrors would need to be lightweight yet durable enough to withstand the harsh conditions of space, including micrometeoroid impacts and extreme temperature fluctuations. Additionally, positioning and maintaining the mirrors in precise orbits would demand sophisticated navigation and control systems, as even small deviations could lead to uneven heating or unintended consequences. Energy requirements are another significant hurdle. The mirrors would need to be powered, and maintaining their alignment and stability over long periods would consume substantial amounts of energy. Solar power could be a potential solution, but generating and storing enough energy to operate the mirrors continuously would be a monumental task. Furthermore, transporting the materials and equipment needed to build these mirrors to a distant exoplanet would require breakthroughs in propulsion technology and logistics. Despite these challenges, the potential benefits of orbital mirrors are undeniable. They offer a relatively non-invasive method of terraforming, as they don't involve introducing foreign substances or drastically altering the planet's atmosphere. Instead, they harness the power of sunlight, a resource that's abundant and renewable, to create conditions favorable for life. This approach could be particularly useful for exoplanets with thick ice layers or those located in colder regions of their star systems. As we consider the possibilities of orbital mirrors, it's clear that this theory represents a blend of creativity and practicality. While the technical obstacles are significant, the potential rewards transforming frozen worlds into thriving habitats make it a compelling avenue for future exploration. Next, we'll delve into the potential risks associated with this method, including the possibility of unintended climate changes and other challenges that could arise from such a large-scale intervention. Now, let's take a closer look at the potential risks associated with using orbital mirrors for terraforming. While the idea of melting ice and creating liquid water on an exoplanet sounds promising, it's important to consider the unintended consequences that could arise from such a large-scale intervention. One of the most significant risks is the possibility of triggering unintended climate changes. By altering the amount of sunlight reaching the planet's surface, we could disrupt its natural climate patterns, leading to unpredictable weather conditions or even extreme temperature fluctuations. For example, too much concentrated sunlight might cause certain regions to overheat, creating deserts or destabilizing ecosystems before they even have a chance to form. Another major concern is the vulnerability of the mirrors themselves. Space is far from empty. It's filled with micrometeoroids, space debris, and radiation. Over time, these hazards could damage the mirrors, reducing their effectiveness or even rendering them useless. A single collision with a piece of debris could shatter a mirror, scattering fragments that might pose additional risks to other spacecraft or the exoplanet's surface. Maintaining and repairing these mirrors over long distances would be a daunting task, requiring advanced robotics or even human intervention, which adds another layer of complexity to the mission. There's also the risk of creating an imbalance in the planet's environment. While melting ice to create water is a key goal, doing so too quickly could lead to flooding or the release of trapped gases such as methane, which could further destabilize the climate. Additionally, if the mirrors are not carefully calibrated, they might inadvertently heat certain areas while leaving others frozen, creating uneven conditions that could hinder the terraforming process. Despite these challenges, it's worth noting that many of these risks could be mitigated with careful planning and advanced technology. For instance, developing self-healing materials for the mirrors or creating redundant systems to ensure their functionality could help address the issue of damage from space debris. Similarly, using advanced climate modeling to predict and manage the effects of increased sunlight could reduce the risk of unintended climate changes. As we weigh the potential benefits and risks of orbital mirrors, it's clear that this approach requires a delicate balance. While the idea holds immense promise for transforming icy exoplanets into habitable worlds, it also demands careful consideration of the potential pitfalls. Next, we'll explore another intriguing theory, the introduction of microbial life to kickstart biological processes on a barren planet. Now, let's shift our focus to a fascinating and somewhat controversial approach to terraforming, the introduction of microbial life. Imagine sending tiny, resilient organisms from Earth to a barren exoplanet, where they could begin the process of transforming its environment. This idea, often referred to as microbial seeding, involves using microbes to kickstart biological processes that could eventually make the planet habitable for humans. But how exactly would this work, and what kinds of microbes could we use? One of the most promising candidates for this task is cyanobacteria. These tiny organisms are often called the workhorses of Earth's early ecosystems because they played a crucial role in producing oxygen through photosynthesis billions of years ago. By introducing cyanobacteria to an exoplanet, we could potentially jumpstart the process of oxygen production, gradually creating a breathable atmosphere. Other microbes like extremophiles, which thrive in Earth's harshest environments, could also be used to break down rocks and release essential nutrients into the soil, laying the groundwork for more complex life forms. The potential impact of microbial seeding is enormous. These tiny organisms could help stabilize the planet's atmosphere, regulate its temperature, and even create organic compounds that future plants and animals could use. Over time, they could transform a lifeless world into one teeming with biological activity. However, this approach isn't without its challenges. For one, we'd need to carefully select microbes that are not only hardy enough to survive the harsh conditions of an exoplanet, but also capable of thriving and reproducing in its unique environment. Another consideration is the speed at which these microbes could affect change. While they might be efficient at producing oxygen or breaking down rocks, the process could take thousands or even millions of years. This raises questions about whether microbial seeding alone would be enough to make an exoplanet habitable within a time frame that aligns with human goals. Still, when combined with other terraforming methods, it could serve as a critical first step in the long journey toward creating a new home for humanity. As we explore the possibilities of microbial seeding, it's clear that this approach offers a unique blend of simplicity and potential. By harnessing the power of Earth's tiniest organisms, we could take the first steps toward transforming a barren world into a thriving ecosystem. Next, we'll delve into the ethical concerns surrounding this method and the risks of contaminating an exoplanet with Earth-based life. Now, let's turn our attention to a critical issue that arises with the idea of microbial seeding, the risk of contamination. Introducing Earth-based microbes to an exoplanet might sound like a groundbreaking step toward terraforming, but it also raises significant ethical and scientific concerns. What if these microbes disrupt or destroy any potential native life forms that we haven't yet discovered? The possibility of contaminating an alien ecosystem is a serious consideration that scientists and ethicists have been grappling with for decades. One of the primary concerns is the concept of planetary protection. This principle, widely upheld by space agencies, emphasizes the need to prevent biological contamination of other celestial bodies. The reasoning is simple. If we introduce Earth-based microbes to an exoplanet, we risk not only altering its environment but also potentially erasing any traces of indigenous life. Even if the planet appears barren, there's always the chance that microbial life could exist beneath its surface or in extreme environments we haven't fully explored. By introducing foreign organisms, we might inadvertently cause irreversible harm to these ecosystems before we even understand them. Another layer of this debate revolves around the ethics of altering another world. Who gets to decide whether an exoplanet should be terraformed? Is it ethical to impose Earth-based life on a planet that might have its own unique evolutionary path? These questions don't have easy answers, but they highlight the need for careful consideration and international collaboration. After all, the decisions we make today could have consequences that last for millennia. There's also the practical challenge of ensuring that the microbes we introduce don't backfire. While we might select organisms like cyanobacteria or extremophiles for their resilience and potential benefits, there's always the risk that they could behave unpredictably in a new environment. For example, they might outcompete any native life forms, disrupt the planet's natural chemical cycles, or even evolve in ways that make them harmful to future human settlers. These uncertainties underscore the importance of thorough research and testing before any microbial seeding mission is launched. Despite these challenges, some argue that the benefits of microbial seeding outweigh the risks. Proponents suggest that if we're careful and deliberate in our approach, we can minimize the chances of contamination while still making progress toward creating a habitable world. They also point out that the search for extraterrestrial life is still in its early stages, and waiting for definitive answers might mean missing out on opportunities to advance human exploration and survival. As we weigh the pros and cons of microbial seeding, it's clear that this approach is as much about ethics and responsibility as it is about science and technology. The decisions we make will shape not only the future of humanity but also our relationship with the cosmos. Next, we'll explore another intriguing theory: the use of artificial magnetic fields to protect a terraformed exoplanet from harmful solar radiation. Now, shifting our focus to a groundbreaking solution for one of the biggest challenges in terraforming, let's explore the concept of artificial magnetic fields. Imagine a terraformed exoplanet, lush with vegetation and teeming with life, but vulnerable to the relentless bombardment of solar radiation. Without a natural magnetic field like Earth's, the planet's atmosphere and surface would be exposed to harmful cosmic rays and solar winds, which could strip away the atmosphere over time and make the planet uninhabitable. This is where artificial magnetic fields come into play. The idea is to create a protective shield around the exoplanet, mimicking Earth's magnetosphere. This shield would deflect charged particles from the sun, preventing them from eroding the atmosphere and harming any potential life forms. But how could we achieve such a feat? One proposed method involves placing a network of superconducting coils in orbit around the planet. These coils would generate a powerful magnetic field, acting as a barrier against solar radiation. Another approach suggests using a large, magnetized satellite positioned at a stable point between the exoplanet and its star, creating a magnetic bubble that shields the planet. The technology required for this is undeniably advanced. Superconducting materials capable of generating and maintaining such strong magnetic fields are still in the experimental stages, and the energy demands would be enormous. We're talking about harnessing power on a scale that far exceeds anything we've achieved on Earth. Additionally, the engineering challenges of constructing and deploying these systems in space are immense. For instance, the coils or satellites would need to be incredibly durable to withstand the harsh conditions of space, and their maintenance over long periods would require innovative solutions. Despite these hurdles, the potential benefits are staggering. An artificial magnetic field could not only protect a terraformed exoplanet, but also extend the window of habitability for billions of years. It could safeguard the atmosphere, preserve liquid water, and create a stable environment for human settlers. Moreover, this technology could be adapted for other purposes, such as protecting spacecraft or even Earth itself from extreme solar events. However, the feasibility of this approach depends on several factors. First, we'd need to develop materials and energy sources capable of sustaining such a massive project. Second, the cost and logistics of transporting and assembling the necessary infrastructure in space would require unprecedented international cooperation and investment. And finally, we'd need to ensure that the magnetic field is stable and adjustable, capable of responding to changes in solar activity without disrupting the planet's environment. As we consider the possibilities, it's clear that artificial magnetic fields represent both a monumental challenge and a transformative opportunity. They could be the key to making distant worlds truly habitable, but realizing this vision will demand innovation, collaboration, and a willingness to push the boundaries of what's possible. Next, we'll delve into the energy requirements for generating and maintaining these artificial magnetic fields and what it would take to power such a system. Now, let's take a closer look at one of the most critical aspects of creating artificial magnetic fields: the energy requirements. Generating and maintaining a magnetic field strong enough to shield an entire exoplanet is no small feat. The energy demands would be astronomical, far beyond anything humanity has ever attempted. To put it into perspective, Earth's natural magnetic field is powered by the planet's molten iron core, a process that has been running continuously for billions of years. Replicating this on an exoplanet would require an energy source capable of sustaining a similar level of output, but without the benefit of a planet's internal heat. One potential solution lies in harnessing nuclear fusion, a process that powers stars and could provide nearly limitless energy. Fusion reactors, if successfully developed, could generate the immense power needed to sustain superconducting coils or magnetized satellites. However, fusion technology is still in its infancy, and achieving a stable, large-scale fusion reaction remains one of the greatest challenges in modern science. Even if we overcome these hurdles, the infrastructure required to build and maintain fusion reactors in space would be incredibly complex and resource-intensive. Another option is to tap into the energy of the exoplanet star. Solar power collected through vast arrays of solar panels or orbital mirrors could provide a renewable energy source. However, the efficiency of solar energy collection decreases with distance from the star, and the sheer scale of the panels needed to power a magnetic field would be staggering. Additionally, storing and distributing this energy across the planet would require advanced battery technology and a robust energy grid, both of which would need to be built from scratch. The energy requirements also raise questions about sustainability. Even if we find a way to generate the necessary power, maintaining it over long periods would be a constant challenge. The systems would need to be highly reliable, with built-in redundancies to prevent catastrophic failures. Any disruption in energy supply could leave the exoplanet vulnerable to solar radiation, undoing years or even centuries of terraforming efforts. Beyond the technical challenges, there's also the issue of cost. The financial investment required to develop, deploy, and maintain such an energy infrastructure would be unprecedented. It would likely require global cooperation and a long-term commitment from multiple nations or private entities. The economic feasibility of this endeavor would depend on the perceived value of creating a habitable exoplanet, as well as the potential benefits it could bring to humanity. Despite these challenges, the potential rewards make this a goal worth pursuing. A stable artificial magnetic field could transform a barren exoplanet into a thriving new home for humanity, offering protection from cosmic threats and ensuring the longevity of its atmosphere. As we continue to explore the possibilities, it's clear that solving the energy puzzle will be a crucial step in making this vision a reality. Next, we'll examine another innovative approach, extracting water from asteroids to create oceans on a dry exoplanet. Now, shifting our focus to another groundbreaking approach, let's explore the concept of extracting water from asteroids to create oceans on a dry exoplanet. Water is essential for life as we know it, and without it, terraforming efforts would be nearly impossible. But what if we could bring water to a barren world by mining it from nearby asteroids or comets? This idea, while ambitious, could be a game-changer in our quest to make distant planets habitable. Asteroids and comets are often rich in water ice, making them prime candidates for this kind of mission. The process would involve identifying suitable targets, sending spacecraft to mine the ice, and then transporting it to the exoplanet. While this sounds straightforward, the logistics are anything but simple. First, we'd need advanced technology to locate and analyze asteroids with high water content. This would require powerful telescopes and sophisticated sensors capable of detecting water from vast distances. Once a suitable asteroid is identified, the next challenge is mining the water. This would involve landing on the asteroid, drilling into its surface and extracting the ice. The equipment needed for this would have to be incredibly durable, capable of operating in the harsh conditions of space, including extreme temperatures and low gravity. After extraction, the water would need to be stored and transported, which introduces another layer of complexity. Spacecraft designed for this purpose would need massive storage tanks and efficient propulsion systems to carry the water across vast distances. Transporting water from an asteroid to an exoplanet would also require precise navigation and timing. The journey could take years depending on the distance, and any miscalculation could result in the loss of the precious cargo. Additionally, the process of delivering the water to the exoplanet's surface would need to be carefully planned. One approach could involve releasing the water into the planet's atmosphere, allowing it to condense and form rain, gradually filling up basins and creating oceans. Alternatively, the water could be deposited directly into pre-existing dry lake beds or craters. However, the challenges don't end there. Even if we successfully deliver the water, we'd need to ensure it remains stable on the exoplanet. Factors like the planet's gravity, temperature, and atmospheric pressure would all play a role in determining whether the water stays liquid or evaporates into space. This means that water extraction alone might not be enough. We'd also need to address other environmental factors to create a sustainable water cycle. Despite these hurdles, the potential benefits are immense. Water extracted from asteroids could provide the foundation for oceans, rivers, and lakes, transforming a dry, lifeless world into a thriving ecosystem. It could also serve as a source of oxygen and hydrogen, essential elements for supporting human life and fueling future exploration. As we continue to push the boundaries of what's possible, the idea of mining water from asteroids offers a tantalizing glimpse into the future of terraforming. Next, we'll delve into the environmental impact of such a mission and the ethical considerations it raises. Now, let's consider the broader implications of extracting water from asteroids and introducing it to an exoplanet. While this approach holds incredible promise, it's crucial to examine the potential environmental consequences of such a dramatic change to a planet's water balance. Altering an exoplanet's ecosystem, even with the best intentions, could have unintended and far-reaching effects. One major concern is the disruption of the planet's natural equilibrium. Introducing large amounts of water could drastically change the surface conditions, potentially triggering geological or climatic shifts. For instance, if water is deposited too quickly, it could lead to flooding, erosion, or even the destabilization of the planet's crust. Over time, this could reshape the landscape in unpredictable ways, creating challenges for future colonization efforts. Another issue is the potential impact on any existing, albeit primitive, ecosystems. Even if an exoplanet appears barren, there's always the possibility of microbial life or other forms of extremophiles that thrive in harsh conditions. Introducing Earth-based water could inadvertently harm these organisms, either by altering their habitat or introducing contaminants. This raises ethical questions about our responsibility to preserve extraterrestrial life, no matter how small or seemingly insignificant. Additionally, the introduction of water could affect the planet's atmosphere. As water evaporates, it could contribute to the formation of clouds and weather patterns, potentially altering the planet's climate. While this might seem beneficial, it could also lead to unintended consequences, such as extreme weather events or changes in temperature that make the planet less hospitable over time. Balancing these changes would require careful planning and monitoring to ensure the planet remains stable and habitable. There's also the question of sustainability. Once water is introduced, how do we ensure it remains a viable resource? If the planet's gravity is too weak, water could escape into space over time, leaving the surface dry once again. Alternatively, if the planet's temperature is too high, water might evaporate rapidly, creating a cycle of loss that's difficult to counteract. Addressing these challenges would require not only advanced technology, but also a deep understanding of the planet's unique characteristics. Finally, we must consider the long-term effects of such a transformation. Terraforming is not a one-time event, but an ongoing process that could take centuries or even millennia. The decisions we make today could have lasting consequences for future generations, both on Earth and on the exoplanet itself. This underscores the importance of approaching terraforming with caution, foresight, and a commitment to minimizing harm. While the idea of creating oceans on a dry exoplanet is undeniably exciting, it's clear that the environmental impact of water extraction must be carefully weighed. As we continue to explore the possibilities of terraforming, we must strive to balance our ambitions with a respect for the delicate systems that govern planetary ecosystems. Next, we'll explore another fascinating theory: how advanced nanotechnology could revolutionize the way we reshape distant worlds. Now, shifting our focus to a groundbreaking approach, let's dive into the fascinating world of nanotechnology and its potential to transform exoplanets. Imagine tiny machines smaller than a grain of sand working together to reshape an entire planet's environment at the molecular level. This is the promise of terraforming via nanotechnology, a concept that could revolutionize how we approach the challenge of making distant worlds habitable. At its core, nanotechnology involves the use of nanobots, microscopic robots designed to perform specific tasks. These machines could be deployed to an exoplanet to carry out a variety of functions, from breaking down harmful compounds in the atmosphere to constructing soil rich in nutrients for plant growth. By operating at such a small scale, nanobots could achieve precision and efficiency that traditional methods simply cannot match. For example, they could target and neutralize toxic gases, converting them into breathable oxygen, or even rearrange molecules to create liquid water from frozen ice. One of the most exciting applications of nanotechnology in terraforming is its ability to accelerate natural processes. On a cold, barren exoplanet, nanobots could be programmed to absorb sunlight and release heat, gradually warming the planet's surface. They could also break down rocks into minerals, releasing trapped gases that could help thicken the atmosphere. Over time, these small but powerful machines could transform a lifeless world into one capable of supporting ecosystems. However, as with any advanced technology, there are significant challenges and limitations to consider. First, the sheer scale of the task is daunting. To terraform an entire planet, we would need trillions of nanobots, each working in perfect harmony. Manufacturing and deploying such a vast number of machines would require unprecedented advancements in production and logistics. Additionally, these nanobots would need to be incredibly durable, capable of surviving harsh conditions like extreme temperatures, radiation, and corrosive atmospheres. Another major concern is control. Once released, nanobots would need to operate autonomously, following pre-programmed instructions without human intervention. This raises the risk of unintended consequences. For instance, if a nanobot malfunctions or deviates from its intended task, it could cause ecological imbalances or even damage the planet's environment. Ensuring the reliability and safety of these machines would be a critical hurdle to overcome. There's also the question of energy. Nanobots would require a constant power source to function, and on a distant exoplanet, this could be a significant challenge. Solar energy might not always be available, especially on planets with long nights or thick atmospheres. Developing efficient and sustainable energy solutions for these machines would be essential to their success. Despite these challenges, the potential of nanotechnology in terraforming is immense. It offers a level of precision and adaptability that could make the dream of habitable exoplanets a reality. By harnessing the power of these tiny machines, we could unlock new possibilities for reshaping worlds and expanding the reach of humanity. As we continue to explore the frontiers of science and technology, the idea of using nanotechnology to terraform exoplanets remains a tantalizing vision. It's a reminder that even the smallest tools can have the biggest impact when applied with creativity and ingenuity. Next, we'll examine the risks associated with this approach and how we might mitigate them to ensure a safe and sustainable future for terraforming. Now, let's take a closer look at the potential risks of using nanotechnology for terraforming. While the possibilities are exciting, it's crucial to consider the dangers that come with deploying such advanced technology on an alien world. One of the most significant concerns is the risk of unintended ecological disruptions. Nanobots designed to manipulate environments at a molecular level could inadvertently harm existing ecosystems or create imbalances that are difficult to reverse. For example, if nanobots were programmed to break down certain compounds but ended up targeting the wrong molecules, they could destabilize the planet's chemistry, leading to unforeseen consequences like toxic atmospheres or barren landscapes. Another major risk is the loss of control over these microscopic machines. Once released, nanobots would operate autonomously, relying on pre-programmed instructions. However, if a malfunction occurs or if the programming is flawed, the nanobots could deviate from their intended tasks. Imagine a scenario where nanobots tasked with warming a planet's surface instead overheated, triggering a runaway greenhouse effect. Or worse, they could begin replicating uncontrollably, consuming resources and potentially damaging the planet's environment beyond repair. Ensuring the reliability and safety of these machines would be a monumental challenge, requiring fail-safes and constant monitoring. Energy dependency is another critical issue. Nanobots would need a steady power source to function, and on a distant exoplanet, this could be a significant hurdle. If the energy supply is interrupted or insufficient, the nanobots could cease functioning, leaving the terraforming process incomplete or even causing the planet to revert to its original state. Additionally, the energy sources themselves could pose risks. For instance, relying on solar power on a planet with long nights or thick cloud cover might not be feasible, forcing us to explore alternative solutions like nuclear energy, which comes with its own set of challenges and dangers. There's also the ethical dimension to consider. Introducing nanotechnology to an exoplanet raises questions about our responsibility as stewards of other worlds. If we accidentally harm a planet's environment or disrupt potential extraterrestrial life, the consequences could be irreversible. The ethical implications of playing such a direct role in reshaping another world must be carefully weighed against the potential benefits. Despite these risks, the potential of nanotechnology in terraforming remains undeniable. The key lies in developing robust safeguards, rigorous testing, and ethical guidelines to minimize the dangers. By addressing these challenges head-on, we can harness the power of nanotechnology responsibly, ensuring that our efforts to create habitable worlds are both effective and sustainable. As we move forward, the balance between innovation and caution will be critical in shaping the future of terraforming. Next, we'll explore how genetic engineering could play a role in transforming exoplanets, offering another fascinating approach to this monumental task. Now, shifting our focus to the role of biology in terraforming, let's explore how genetic engineering of plants could revolutionize our ability to create habitable environments on exoplanets. Imagine a world where plants are not just passive inhabitants but active participants in shaping a planet's atmosphere and ecosystem. By modifying the genetic makeup of plants, we could design species capable of thriving in harsh alien conditions while producing oxygen and stabilizing the environment. This approach, often referred to as synthetic biology, offers a promising pathway to transform barren landscapes into lush, life-supporting worlds. The science behind this idea is rooted in our understanding of photosynthesis, the process by which plants convert carbon dioxide into oxygen using sunlight. On Earth, plants have evolved over millions of years to optimize this process for our specific environment. However, exoplanets present vastly different conditions, extreme temperatures, varying light intensities, and unfamiliar soil compositions. Genetic engineering allows us to tailor plants to these unique challenges. For instance, we could enhance their ability to photosynthesize under dimmer light or equip them with traits that enable survival in low-nutrient soils. By introducing genes from extremophiles organisms that thrive in Earth's harshest environments, we could create plants capable of withstanding the extreme conditions of an alien world. One of the most exciting possibilities is engineering plants to produce higher amounts of oxygen. By tweaking the genes responsible for photosynthesis, scientists could potentially increase the efficiency of oxygen production, accelerating the process of creating a breathable atmosphere. Additionally, these plants could be designed to absorb and store large amounts of carbon dioxide, helping to regulate the planet's climate and prevent runaway greenhouse effects. Over time, these genetically modified plants could form the foundation of a self-sustaining ecosystem, paving the way for more complex life forms to thrive. However, this approach is not without its challenges. One major hurdle is ensuring the stability and safety of genetically engineered plants in an alien environment. Unlike Earth, where ecosystems have evolved intricate checks and balances, an exoplanet's environment would be unpredictable. Introducing engineered plants could lead to unintended consequences, such as outcompeting native species, if any exist, or disrupting the planet's delicate chemical balance. There's also the risk of genetic mutations over time, which could alter the plant's behavior and potentially render them ineffective or harmful. Another challenge lies in the logistics of transporting and cultivating these plants on a distant exoplanet. Seeds or plant samples would need to survive the journey through space, withstand the rigors of landing, and then adapt to the planet's surface conditions. This would require advanced technologies for preserving and nurturing plant life during transit, as well as robotic systems capable of planting and maintaining these species on an alien world. Energy and resource constraints could further complicate these efforts, especially on planets with limited sunlight or water. Despite these obstacles, the potential of genetic engineering in terraforming is immense. By harnessing the power of biology, we could create ecosystems that not only support human life, but also contribute to the long-term sustainability of an exoplanet. As we continue to explore this frontier, the integration of genetic engineering with other terraforming strategies could unlock new possibilities for transforming distant worlds into second homes for humanity. Next, we'll delve into the ethical concerns surrounding the use of genetically modified organisms in terraforming, examining the moral implications of reshaping life on another planet. Now, let's turn our attention to the ethical considerations that come with the use of genetically modified organisms in terraforming. While the scientific possibilities are thrilling, the moral implications of reshaping life on another planet raise important questions that demand careful reflection. At the heart of this debate is the idea of altering ecosystems that may already exist, even in the most rudimentary forms. If an exoplanet harbors microbial life or other organisms, introducing genetically engineered plants could disrupt or even destroy these native species. This raises a fundamental ethical dilemma. Do we have the right to impose Earth-based life on another world, potentially at the expense of its own evolutionary path? Another concern is the potential for unintended consequences. Genetic engineering, while powerful, is not an exact science. Even on Earth, where we have a deep understanding of ecosystems, introducing genetically modified organisms has sometimes led to unforeseen ecological disruptions. On an exoplanet where conditions are entirely alien, the risks could be even greater. Engineered plants might behave unpredictably, spreading uncontrollably or interacting with the environment in ways we can't anticipate. This could lead to ecological imbalances that undermine the very goals of terraforming, creating a hostile environment rather than a habitable one. There's also the question of responsibility. If we succeed in terraforming an exoplanet and establishing human colonies, who will oversee the long-term management of these engineered ecosystems? Ensuring that they remain stable and sustainable over generations would require ongoing monitoring and intervention. This raises concerns about the ethical burden we place on future generations, who may inherit the consequences of our actions without having had a say in the decisions that shaped their world. Moreover, the act of genetically engineering life for another planet touches on deeper philosophical questions about humanity's role in the universe. Are we stewards of life with a responsibility to preserve and nurture it wherever we find it, or are we explorers free to reshape worlds in our image? These questions don't have easy answers, but they are essential to consider as we move forward with technologies that could fundamentally alter the fabric of other planets. As we weigh these ethical concerns, it's important to remember that the pursuit of terraforming is not just a scientific endeavor, it's a deeply human one. The choices we make will reflect our values and priorities as a species. By engaging in thoughtful, inclusive discussions about the ethics of genetic engineering, we can ensure that our efforts to expand beyond Earth are guided by both ambition and responsibility. Next, we'll explore another fascinating approach to terraforming, the use of artificial photosynthesis to create breathable atmospheres on exoplanets. Now, let's shift our focus to a groundbreaking approach that could revolutionize how we create breathable atmospheres on distant worlds: artificial photosynthesis. Imagine a technology that mimics the natural process plants use to convert carbon dioxide into oxygen, but on a scale large enough to transform an entire exoplanet. This concept isn't just science fiction. It's a scientifically plausible method that could play a key role in making alien worlds habitable for humans. Artificial photosynthesis works by using advanced materials and systems to replicate the way plants absorb sunlight, carbon dioxide, and water to produce oxygen. On Earth, scientists have already developed prototypes of artificial leaves and other devices that can perform this process. These technologies rely on specialized catalysts and light-absorbing materials to drive the chemical reactions needed to split water molecules and release oxygen. If scaled up, similar systems could be deployed on an exoplanet to gradually build up an oxygen-rich atmosphere. One of the biggest advantages of artificial photosynthesis is its potential efficiency. Unlike natural plants, which require specific conditions to thrive, artificial systems can be designed to operate in a wide range of environments. They could function in low light conditions, extreme temperatures, or even in the presence of toxic gases, conditions that would be fatal to most Earth-based life. This adaptability makes artificial photosynthesis a promising tool for terraforming planets with harsh or unpredictable climates. However, the technology isn't without its challenges. Creating systems that can operate reliably over long periods in alien environments would require significant advancements in materials science and engineering. The devices would need to be durable enough to withstand radiation, dust storms, and other planetary hazards. Additionally, producing and transporting the necessary materials to an exoplanet would be a massive logistical undertaking, requiring breakthroughs in space travel and resource utilization. Another consideration is the time it would take to generate a breathable atmosphere. Even with highly efficient systems, the process of converting an exoplanet's carbon dioxide into oxygen would likely take decades, if not centuries. This raises questions about how we would sustain such long-term projects and whether future generations would be willing to continue the work started by their predecessors. Despite these challenges, the potential benefits of artificial photosynthesis are immense. Not only could it provide a sustainable way to produce oxygen, but it could also help regulate an exoplanet's climate by reducing greenhouse gases. Over time, this could create a more stable and hospitable environment for human colonization. As we explore the possibilities of artificial photosynthesis, it's clear that this technology represents a fusion of innovation and ambition. It challenges us to think creatively about how we can harness the power of science to reshape worlds. Next, we'll delve into the scalability of this approach and the hurdles we'll need to overcome to make it a reality on a planetary scale. Now, let's take a closer look at what it would take to scale artificial photosynthesis to a planetary level. While the concept of using artificial systems to produce oxygen on an exoplanet is exciting, the sheer scale of such an endeavor presents significant challenges. Imagine trying to cover an entire planet with enough devices to generate a breathable atmosphere. This isn't just a matter of building a few machines. It's about creating an infrastructure capable of transforming a world. One of the first hurdles is the sheer number of devices required. To produce enough oxygen for a planet, we'd need millions, if not billions, of artificial photosynthesis units. Each of these units would need to be durable, efficient, and capable of operating in the harsh conditions of an alien environment. Designing and manufacturing these devices on such a massive scale would require unprecedented advancements in materials science and production techniques. We're talking about creating technology that can be mass-produced, transported across space, and deployed across vast, uninhabited landscapes. Energy is another critical factor. Artificial photosynthesis systems rely on sunlight to drive the chemical reactions that produce oxygen. On a planet with limited sunlight or long periods of darkness, this could pose a serious problem. We'd need to develop energy storage solutions or alternative power sources to keep these systems running consistently. Solar panels, nuclear reactors, or even advanced batteries could play a role, but each of these options comes with its own set of challenges and limitations. Then there's the issue of maintenance. Over time, these devices would inevitably wear down due to exposure to radiation, dust, and other environmental factors. Keeping billions of units operational would require a robust maintenance system, possibly involving autonomous robots or remote-controlled repair units. This adds another layer of complexity to an already daunting task. Even if we overcome these technical challenges, there's the question of time. Scaling up artificial photosynthesis to cover an entire planet wouldn't happen overnight. It could take centuries to produce enough oxygen to make an exoplanet habitable. This raises important questions about how we would manage such a long-term project. Would future generations be willing to continue the work started by their ancestors? And how would we ensure that the technology remains effective over such an extended period? Despite these challenges, the potential rewards are immense. If we can successfully scale artificial photosynthesis, we could create a self-sustaining system that not only produces oxygen but also helps regulate an exoplanet's climate. Over time, this could transform a barren world into a thriving ecosystem capable of supporting human life. As we consider the scalability of artificial photosynthesis, it's clear that this approach requires not just technological innovation but also a long-term vision. It challenges us to think beyond our current capabilities and imagine a future where humanity has the tools to reshape entire worlds. Next, we'll explore another fascinating idea, the concept of underground habitats and how they could provide a safe haven for humans while terraforming efforts are underway. Now, shifting our focus to a different approach, let's explore the concept of underground habitats. While terraforming an exoplanet is a monumental task that could take centuries, humans would need a safe place to live during this long process. Underground habitats offer a practical solution, shielding us from the planet's harsh surface conditions, such as extreme temperatures, radiation, or toxic atmospheres. But building a livable environment beneath the surface comes with its own set of challenges, both technical and psychological. First, let's consider the engineering hurdles. Constructing underground habitats requires advanced excavation techniques and materials capable of withstanding immense pressure from the surrounding rock and soil. We'd need to create vast networks of tunnels, chambers, and life support systems, all while ensuring structural integrity and safety. This would involve not only digging deep into the planet's crust, but also designing habitats that can maintain stable temperatures, air quality, and humidity levels. Technologies like 3D printing or autonomous mining robots could play a crucial role in making this feasible, but scaling these solutions to support entire populations would be a massive undertaking. Energy is another critical factor. Underground habitats would need reliable power sources to sustain lighting, heating, and life support systems. Solar energy might not be an option, so we'd have to rely on alternatives like geothermal energy, nuclear reactors, or advanced battery systems. Each of these options has its own complexities, from managing heat dissipation in confined spaces to ensuring long-term energy storage. But beyond the technical challenges, there's the human element to consider. Living underground for extended periods could have significant psychological effects. Humans are naturally drawn to open spaces, sunlight, and natural environments. Being confined to underground habitats could lead to feelings of isolation, claustrophobia, or even depression. To address this, we'd need to design habitats that mimic natural environments as much as possible. This could include artificial lighting that replicates daylight, green spaces with plants, and recreational areas to promote mental well-being. Virtual reality might also play a role, offering immersive experiences of outdoor environments to help residents feel connected to the world above. Another consideration is the social dynamics of living in such close quarters. Underground habitats would likely house large populations in relatively confined spaces, which could lead to tensions or conflicts over resources, privacy, or decision-making. Establishing effective governance structures and community-building initiatives would be essential to maintaining harmony and ensuring the long-term success of these habitats. Despite these challenges, underground habitats offer a promising way to protect humans while terraforming efforts are underway. They provide a controlled environment where we can survive and thrive, even on a planet with an inhospitable surface. Over time, as terraforming progresses, these habitats could serve as a bridge, allowing us to gradually transition to living on the surface. As we think about the possibilities of underground living, it's clear that this approach requires not just technological innovation, but also a deep understanding of human needs and behavior. It challenges us to rethink how we design living spaces and how we adapt to life in entirely new environments. Next, we'll delve into the long-term viability of underground living and explore how humans might cope with the psychological and social challenges of life beneath the surface. Now, let's take a closer look at the long-term viability of underground living. While these habitats offer a practical solution for surviving harsh exoplanet conditions, we must consider how humans would adapt over extended periods. One of the most pressing concerns is mental health. Humans are naturally drawn to open spaces, sunlight, and natural environments, and being confined underground for years or even decades could lead to significant psychological challenges. Feelings of isolation, claustrophobia, and depression could become widespread, especially if residents are unable to experience the outdoors or see the sky. To combat this, habitats would need to incorporate advanced psychological support systems, such as therapy programs, community activities, and even virtual reality simulations of outdoor environments to help residents feel connected to nature. Resource limitations are another critical factor. Underground habitats would need to be entirely self-sufficient, relying on carefully managed supplies of food, water, and energy. Over time, maintaining these resources could become increasingly difficult, especially if the population grows or if terraforming efforts take longer than expected. Recycling systems would need to be highly efficient, and food production would likely depend on advanced hydroponics or lab-grown alternatives. Energy sources such as geothermal or nuclear power would need to be sustainable and capable of meeting the demands of a growing population. Any disruptions to these systems could have severe consequences, making redundancy and backup plans essential. Social dynamics also play a significant role in the long-term success of underground living. Living in close quarters with limited personal space could lead to tensions or conflicts over resources, privacy, or decision-making. Establishing effective governance structures and fostering a sense of community would be crucial to maintaining harmony. Regular communication, conflict resolution mechanisms, and opportunities for social interaction would help prevent isolation and promote cooperation among residents. Another consideration is the potential for generational adaptation. If terraforming takes centuries, multiple generations could be born and raised in underground habitats. Over time, these generations might adapt to their environment, developing new cultural norms and ways of life. However, this raises questions about how these communities would eventually transition to living on the surface. Would they retain a connection to their underground origins, or would they embrace the new environment entirely? These cultural and psychological shifts would need to be carefully managed to ensure a smooth transition. Despite these challenges, underground living remains a viable option for supporting human life during the long process of terraforming. It offers a controlled environment where we can survive and thrive, even on a planet with an inhospitable surface. By addressing the psychological, social, and resource-related challenges, we can create habitats that not only sustain life but also foster resilience and adaptability. As we continue to explore the possibilities of terraforming, underground habitats could serve as a crucial stepping stone, helping humanity bridge the gap between survival and thriving on a new world. Next, we'll examine another fascinating approach: the idea of using controlled asteroid impacts to release trapped gases or water on an exoplanet. Now, shifting our focus to a more dramatic approach, let's explore the idea of using controlled asteroid impacts to terraform exoplanets. This method involves carefully directing asteroids to collide with a planet's surface, releasing trapped gases or water that could help create a more habitable environment. The concept is both bold and scientifically intriguing, as it leverages the natural resources of space to kickstart planetary transformation. By targeting specific areas such as ice caps or regions rich in underground gases, these impacts could potentially unlock the building blocks needed for a stable atmosphere and liquid water. One of the key benefits of this approach is its potential to rapidly alter a planet's conditions. Unlike other methods that may take centuries, asteroid impacts could release significant amounts of water vapor or greenhouse gases in a relatively short time. For example, striking an icy region could melt large quantities of frozen water, creating lakes or even oceans. Similarly, impacting areas with trapped carbon dioxide or methane could help thicken the atmosphere, warming the planet and making it more suitable for life. This method could serve as a powerful tool to jumpstart the terraforming process, especially on planets that are cold or lack sufficient surface water. However, the risks associated with asteroid impacts are equally significant. One major concern is the potential for unintended consequences, such as triggering volcanic activity or destabilizing the planet's climate. A poorly planned impact could release too much gas too quickly, leading to runaway greenhouse effects or extreme weather patterns. Additionally, the force of the collision could create massive dust clouds, blocking sunlight and cooling the planet's surface, which might counteract the intended warming effects. These risks highlight the importance of precise calculations and careful planning to ensure the impacts achieve the desired results without causing long-term harm. Another challenge is the sheer scale of engineering required to execute such a plan. Redirecting asteroids to specific targets would demand advanced propulsion systems and precise navigation, as even a slight miscalculation could result in catastrophic outcomes. Moreover, the energy needed to alter an asteroid's trajectory is immense, raising questions about the feasibility of this approach with current technology. While the idea is theoretically sound, practical implementation would require significant advancements in space engineering and resource management. Despite these challenges, the potential rewards of asteroid impacts make them a compelling option for terraforming. By harnessing the natural power of these celestial bodies, we could unlock resources that are otherwise inaccessible, accelerating the process of making an exoplanet habitable. As we continue to explore the possibilities of terraforming, this method reminds us of the incredible potential and risks of reshaping entire worlds. Next, we'll delve into another innovative strategy: the use of massive solar shields to protect a terraforming exoplanet from harmful radiation. Now, let's take a closer look at the risks involved with using asteroid impacts as a terraforming tool. While the idea of releasing trapped gases or water through controlled collisions sounds promising, the potential dangers cannot be ignored. One of the most significant risks is the possibility of triggering volcanic activity. The force of an asteroid impact could destabilize a planet's crust, leading to eruptions that release massive amounts of lava, ash, and toxic gases. This could not only disrupt the terraforming process, but also create hazardous conditions that make the planet even less habitable than before. Another major concern is the risk of creating unstable climates. An asteroid impact could release large quantities of greenhouse gases too quickly, causing a runaway greenhouse effect. This might lead to extreme temperature swings, making it difficult to establish a stable environment for human life. For instance, if too much carbon dioxide is released at once, the planet could overheat, evaporating any newly formed water sources and rendering the surface uninhabitable. On the other hand, if the impact generates excessive dust clouds, they could block sunlight for extended periods, plunging the planet into a prolonged cold spell. Both scenarios highlight the delicate balance required to achieve the desired outcomes without causing unintended harm. The unpredictability of asteroid impacts also raises questions about their long-term effects. Even with precise calculations, the complex interactions between an impact and a planet's geology and atmosphere are difficult to fully predict. A single miscalculation could result in catastrophic consequences, such as triggering earthquakes or altering the planet's magnetic field. These uncertainties underscore the need for thorough research and advanced modeling before attempting such a high-stakes approach. Finally, there's the ethical dimension to consider. Deliberately altering an exoplanet's environment through asteroid impacts could have irreversible effects, potentially destroying any existing ecosystems or unique geological features. This raises important questions about humanity's responsibility when intervening in extraterrestrial environments. Should we prioritize our survival over preserving the natural state of other worlds? These ethical dilemmas add another layer of complexity to the already challenging task of terraforming. While asteroid impacts offer a fascinating and potentially powerful method for transforming exoplanets, the risks involved remind us of the immense responsibility that comes with reshaping entire worlds. As we continue to explore these possibilities, it's crucial to weigh the potential benefits against the dangers, ensuring that our efforts to create new homes among the stars are both effective and ethical. Next, we'll turn our attention to another innovative strategy: the use of massive solar shields to protect a terraforming exoplanet from harmful radiation. Now, shifting our focus to a different approach, let's explore the concept of solar radiation shielding. Imagine constructing massive shields in space to protect a terraforming exoplanet from harmful solar radiation. This idea, while ambitious, could be a game-changer in making hostile worlds more habitable. The primary goal of these shields would be to block or deflect the intense radiation from a star, which can otherwise strip away a planet's atmosphere or make its surface uninhabitable. By creating a barrier between the exoplanet and its star, we could create a safer environment for both the planet's evolving ecosystem and future human settlers. The engineering behind such a project is nothing short of monumental. These shields would need to be enormous, potentially spanning thousands of kilometers, to effectively block radiation on a planetary scale. They would also need to be positioned at a stable point in space, such as a Lagrange point, where the gravitational forces of the star and the planet balance out. This would allow the shield to remain in a fixed position relative to the planet, ensuring continuous protection. However, constructing and deploying such a massive structure would require advanced materials and technologies that are currently beyond our capabilities. For instance, the shield would need to be lightweight yet durable enough to withstand the harsh conditions of space, including micrometeoroid impacts and extreme temperature fluctuations. One of the most promising benefits of solar radiation shielding is its potential to stabilize a planet's climate. By reducing the amount of radiation reaching the surface, we could prevent excessive heating and create more temperate conditions. This would be particularly useful for planets orbiting stars that emit high levels of ultraviolet or X-ray radiation, which can be detrimental to both biological life and technological infrastructure. Additionally, shielding could help preserve a planet's atmosphere by reducing the rate of atmospheric loss caused by radiation-driven processes. Over time, this could create a more stable environment, paving the way for further terraforming efforts. However, the challenges don't end with construction and deployment. Maintaining these shields over long periods would be a significant hurdle. Space is filled with debris and radiation that could damage the shield over time, requiring regular repairs and upgrades. Moreover, the energy required to keep the shield in position and functional would be immense, raising questions about the sustainability of such a project. These challenges highlight the need for innovative solutions and international collaboration to make solar radiation shielding a viable option for terraforming. Despite the obstacles, the potential benefits of this approach are too significant to ignore. By protecting an exoplanet from harmful radiation, we could create a safer and more stable environment for future generations. This method also offers a less invasive alternative to other terraforming techniques, as it doesn't require altering the planet's surface or atmosphere directly. As we continue to explore the possibilities of terraforming, solar radiation shielding stands out as a promising strategy that combines cutting-edge engineering with the dream of making distant worlds our new homes. Next, we'll delve into the challenges of maintaining these shields over time and the implications for long-term terraforming efforts. Now, let's take a closer look at what it would take to keep these solar shields operational over the long term. Maintaining such massive structures in the harsh environment of space is no small feat. Over time, the shields would face constant threats from micrometeoroids, space debris, and even the relentless bombardment of solar radiation itself. Even the most durable materials would degrade under these conditions, requiring regular inspections and repairs to ensure the shields remain effective. One of the biggest challenges is the sheer scale of these shields. Imagine trying to monitor and repair a structure that spans thousands of kilometers, all while it's positioned millions of kilometers away from Earth. Traditional methods of maintenance, like sending repair crews, would be impractical due to the vast distances involved. Instead, we'd likely rely on advanced robotics and autonomous systems to handle repairs. These machines would need to be incredibly precise and resilient, capable of operating in the vacuum of space and withstanding extreme temperatures. Energy is another major concern. Keeping the shields in position and functional would require a constant supply of power. Solar energy could be a potential solution, but even that comes with its own set of challenges. The shields would need to be equipped with highly efficient solar panels and energy storage systems to ensure they can operate continuously, even during periods of reduced sunlight. Additionally, any power system would need to be shielded itself to prevent damage from the very radiation it's designed to block. Then there's the issue of coordination. Maintaining these shields would likely require a global effort involving multiple nations and organizations working together. This level of collaboration would be unprecedented, and it would demand not only technological innovation but also diplomatic coordination. The cost of such a project would be astronomical, raising questions about funding and resource allocation. Who would bear the financial burden, and how would the benefits be shared? These are questions that would need to be addressed long before any shield is deployed. Despite these challenges, the potential rewards make the effort worthwhile. A well-maintained solar shield could protect a terraforming exoplanet for centuries, providing a stable environment for both ecosystems and human settlers. It's a reminder that while the road to terraforming is filled with obstacles, each challenge we overcome brings us one step closer to making distant worlds our new homes. Next, we'll explore another fascinating approach, using algae blooms to kickstart the terraforming process and create a breathable atmosphere. Now, let's dive into a fascinating and natural approach to terraforming, using algae blooms to transform an exoplanet's atmosphere. Algae, those tiny but mighty organisms, could play a crucial role in making a distant world habitable. By introducing algae to an exoplanet's oceans, we could kickstart a process that not only produces oxygen but also absorbs carbon dioxide, effectively creating a breathable atmosphere over time. The science behind this idea is rooted in how algae function on Earth. Algae are photosynthetic organisms, meaning they use sunlight to convert carbon dioxide and water into oxygen and organic compounds. On a terraformed exoplanet, algae could be introduced to large bodies of water, where they would multiply rapidly, forming massive blooms. These blooms would absorb carbon dioxide from the atmosphere, reducing greenhouse gases, while simultaneously releasing oxygen as a byproduct. Over time, this process could help stabilize the planet's climate and make the air breathable for humans. One of the key advantages of using algae is their simplicity and efficiency. Unlike more complex organisms, algae require minimal resources to thrive. They can survive in a wide range of temperatures and salinity levels, making them adaptable to various exoplanetary conditions. Additionally, algae reproduce quickly, meaning they could cover vast areas of an exoplanet's oceans in a relatively short amount of time. This rapid growth would accelerate the terraforming process, potentially reducing the time needed to create a habitable environment. However, the success of this approach depends on several factors. First, the exoplanet would need to have liquid water, as algae require it to survive. Second, the planet's surface would need to receive sufficient sunlight to fuel photosynthesis. Finally, the algae would need to be carefully selected or engineered to thrive in the specific conditions of the target exoplanet. For example, if the planet has lower light levels than Earth, we might need to develop algae strains that are more efficient at photosynthesis under dimmer conditions. Despite these challenges, the potential of algae blooms as a terraforming tool is immense. They offer a natural, self-sustaining way to transform an exoplanet's atmosphere, with the added benefit of creating a foundation for more complex ecosystems to develop. As we continue to explore the possibilities of terraforming, algae could prove to be one of the most effective and environmentally friendly tools at our disposal. Next, we'll examine the potential risks of this approach and how we might mitigate them to ensure a successful terraforming process. Now, let's shift our focus to the potential risks of using algae blooms as a terraforming tool. While the idea of harnessing these tiny organisms to create a breathable atmosphere is promising, it's not without its challenges. One of the most significant concerns is the possibility of uncontrolled growth. Algae reproduce rapidly, and if their population isn't carefully managed, they could overwhelm an exoplanet's ecosystems. This unchecked growth might lead to massive algal blooms that deplete oxygen levels in the water, creating dead zones where other forms of life cannot survive. Such an imbalance could disrupt the very ecosystems we're trying to build, making the planet less habitable rather than more. Another risk lies in the potential for ecological disruption. Introducing Earth-based algae to an exoplanet could have unintended consequences for any native microorganisms that might already exist. Even if the planet appears barren, there's always the possibility of microbial life forms that we haven't yet detected. Introducing foreign algae could outcompete or even wipe out these native species, leading to a loss of biodiversity before we even begin to understand the planet's natural ecosystems. This raises ethical questions about our right to alter another world's environment, especially if it already harbors life, no matter how simple. Additionally, algae blooms could have unintended effects on the planet's climate. While they absorb carbon dioxide, their rapid growth and eventual decay could release other greenhouse gases, such as methane, into the atmosphere. This could counteract the benefits of carbon dioxide reduction and potentially destabilize the climate further. Managing these side effects would require careful monitoring and intervention, adding complexity to the terraforming process. To mitigate these risks, scientists would need to develop precise control mechanisms. For example, genetically engineered algae could be designed to self-regulate their population growth or to break down harmlessly after a certain period. Advanced monitoring systems would also be essential to track the algae's impact on the environment and make adjustments as needed. By anticipating these challenges and planning for them, we can increase the likelihood of success while minimizing potential harm. As we continue to explore the possibilities of terraforming, it's clear that algae blooms offer both incredible potential and significant risks. Balancing these factors will be key to creating a sustainable and habitable environment on distant worlds. Next, we'll turn our attention to another innovative approach: the concept of artificial weather systems and how they could be used to regulate an exoplanet's climate. Now, let's dive into the fascinating concept of artificial weather systems and how they could revolutionize the way we terraform exoplanets. Imagine being able to control the climate of an entire planet, tailoring it to create the perfect conditions for human life. This idea might sound like science fiction, but with advancements in technology, it's becoming a plausible strategy for future terraforming efforts. Artificial weather systems would involve creating and managing weather patterns on a planetary scale. This could include generating rain to fill dry riverbeds, dispersing clouds to allow sunlight to reach the surface, or even controlling wind patterns to stabilize temperatures. The technology required for such a feat would be incredibly advanced, relying on a combination of atmospheric manipulation, energy generation, and precise monitoring systems. For example, massive arrays of satellites or ground-based installations could be used to influence weather patterns by altering air pressure, temperature, or humidity levels in specific regions. One of the key challenges in developing artificial weather systems is the sheer scale of energy required. Manipulating weather on a planetary level would demand vast amounts of power, likely sourced from advanced nuclear reactors, solar arrays, or even fusion technology. Additionally, the systems would need to be highly efficient and capable of operating continuously over long periods. This raises questions about the feasibility of such technology, especially when considering the logistical challenges of transporting and maintaining these systems on a distant exoplanet. Another consideration is the potential for unintended consequences. Weather systems are incredibly complex, and even small changes can have far-reaching effects. For instance, altering wind patterns to cool one region might inadvertently cause droughts or storms in another. This means that any artificial weather system would need to be carefully designed and constantly monitored to ensure it achieves the desired outcomes without disrupting the planet's overall climate balance. Despite these challenges, the potential benefits of artificial weather systems are immense. By controlling an exoplanet's climate, we could create stable, habitable environments much faster than through natural processes. This could significantly reduce the time required for terraforming, making it possible to establish human colonies on distant worlds within a more realistic time frame. Moreover, the ability to regulate weather could help mitigate the risks of extreme climate events, such as hurricanes or prolonged droughts, which could otherwise threaten the success of a terraforming project. As we look to the future, artificial weather systems represent a bold and innovative approach to terraforming. While the technology is still in its early stages, the possibilities it offers are truly exciting. Next, we'll explore the challenges of implementing these systems and the potential hurdles we'll need to overcome to make this vision a reality. Now, let's take a closer look at the challenges of controlling artificial weather systems on a planetary scale. While the idea of shaping an exoplanet's climate is undeniably exciting, the reality of implementing such systems comes with significant hurdles. One of the most pressing issues is the complexity of weather itself. Earth's climate is a delicate balance of countless variables, from temperature and humidity to wind patterns and ocean currents. Replicating or manipulating these factors on another planet would require an unprecedented level of precision and coordination. A major obstacle is the unpredictability of weather systems. Even with advanced technology, predicting how a small change in one area might affect the entire planet is incredibly difficult. For example, adjusting rainfall in one region could inadvertently disrupt atmospheric pressure elsewhere, leading to unforeseen storms or droughts. This means that any artificial weather system would need to be equipped with real-time monitoring and adaptive controls to respond to unexpected changes. The computational power required to process such vast amounts of data and make instantaneous adjustments would be staggering. Another challenge lies in the energy demands of these systems. As mentioned earlier, manipulating weather on a planetary scale would require an enormous amount of energy. While advanced energy sources like fusion reactors or massive solar arrays could potentially meet these needs, the infrastructure required to build and maintain them on an exoplanet would be a monumental task. Transporting the necessary materials and equipment across interstellar distances adds another layer of complexity, making the logistics of such a project daunting. Additionally, there's the issue of long-term sustainability. Artificial weather systems would need to operate continuously for decades, if not centuries, to achieve and maintain a stable climate. This raises questions about the durability of the technology and the ability to repair or upgrade it over time. Any malfunction or failure could have catastrophic consequences, potentially undoing years of terraforming efforts and jeopardizing the survival of any human colonies. Finally, there's the ethical dimension to consider. Deliberately altering an exoplanet's climate carries the risk of unintended ecological consequences. If the planet has any form of microbial life or unique geological features, artificial weather systems could disrupt or destroy them. This raises important questions about our responsibility as stewards of other worlds and the potential consequences of our actions. Despite these challenges, the pursuit of artificial weather systems represents a bold step forward in our quest to terraform exoplanets. While the road ahead is fraught with difficulties, the potential rewards creating habitable worlds for future generations are worth the effort. As we continue to explore this concept, we'll need to address these challenges head-on, combining innovation, collaboration, and careful planning to turn this vision into reality. Next, we'll shift our focus to another groundbreaking idea: terraforming via algae blooms and how they could play a crucial role in shaping the future of exoplanet colonization. As we wrap up our exploration of the 25 specific theories on how exoplanets could be terraformed for human life, it's clear that the possibilities are as vast as the universe itself. From atmospheric manipulation and greenhouse gas seeding to the use of orbital mirrors, microbial life, and artificial magnetic fields, each theory offers a unique glimpse into the future of interstellar colonization. We've also delved into the challenges energy demands, ethical concerns, technological limitations, and the sheer complexity of altering entire worlds. These hurdles remind us that while the dream of terraforming is within reach, it will require unprecedented innovation, collaboration, and perseverance. The journey to make distant planets habitable is not just about science and technology. It's about humanity's enduring spirit of exploration and our desire to thrive beyond the confines of Earth. Each theory we've discussed represents a step toward a future where humanity could call multiple worlds home. Whether it's melting ice with orbital mirrors, creating artificial weather systems, or seeding oceans with algae, the ideas we've explored are a testament to human ingenuity and our relentless pursuit of progress. But this is just the beginning. The challenges are immense and the road ahead is long, but the potential rewards are nothing short of extraordinary. Imagine a future where humanity spreads across the stars, building civilizations on worlds we once thought unreachable. It's a vision that inspires hope, curiosity, and a sense of shared purpose. Now we want to hear from you. What do you think about these theories? Which one excites you the most, and which challenges do you think are the most daunting? Share your thoughts in the comments below. Let's continue this conversation and dream together about the incredible possibilities that lie ahead. Don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update as we explore more groundbreaking ideas about the future of humanity and the cosmos. Thank you for joining us on this journey, and remember, the stars are not the limit, they're just